So chapter 12 is all about solids, and we've talked about these before. And so, what we've learned before was there's a fixed shape, there's a fixed volume. They're going to hold a shape, they're going to hold a size. They're not going to fill a container. They're not going to fit the shape of a container. They are the container, right? They're the solid object. So not a liquid, not a gas. And then they're also very dense. The constituent particles are very closely packed together, and that leads to lots of intermolecular interactions. So the chapter 10 ideas are going to very much be in play in this chapter. We're going to talk about intermolecular forces, and actually basically every intermolecular force leads to a different class of solid, as you'll see in the figure I'm going to zoom in on in a minute. So how are we going to expand on this? What are we going to cover that's new in this chapter? Well, we're going to talk about the different types of solids, atomic, metallic, etc., and we'll do that in this video. And, well, there'll be a few more we talk about in subsequent videos, but the basic general categories in this one. And then the kind of atomic or molecular, depending on if it's an atomic or molecular solid or ionic solid, and the organization or stacking patterns of the particles. And that'll be in the next video primarily. It'll be, we'll talk about the unit cell and what that is and how we could figure out a formula from it, so on and so forth. And so I'm going to rely very heavily on imagery from your textbook and a little bit from the internet in this chapter. Typically, I spend a lot of time in front of the projector on this chapter. There's not a lot of stuff I can really draw on a board, so this will all be screen capture in this chapter. And it will be a little bit lighter of a chapter than you're used to. The exam for this chapter is only going to be 25 points. It'll be 12 questions, so it's a little bit of kind of like it's more of a half-week subject normally, but I'll stretch it over the whole week. I ran you guys pretty hard through the first couple chapters, so I'll give you a little bit of a break before we get into the last leg of the class here, as kinetics and equilibrium are difficult subjects, and so I want to make sure we have 2 weeks for each of those. But I'll give you a little bit of time to reorient yourselves, your internal compasses or whatever, and before we get started on that. So this isn't a super difficult chapter, but there are some key ideas in it, and it really leans on some older material too. So just a heads up on that. All right, so if we look at table 12.1 from your textbook, the first thing is we have all these different types of solids. And the first major breakdown is we have crystalline solids. And these are just organized stacking structures that repeat over and over again. Like there is a pattern, there is a process. And then the other example is amorphous solids. And most solids are crystalline. And amorphous solids are made a little bit trickier by the fact that it used to be that the classic example was glass. And I don't know if volcano glass falls in this category or not, but actually, yeah, it would. So, the type of glass that we use in windows and things like that is silicon dioxide. So yeah, this would be an example of that. And it turns out that that's not an amorphous solid. And for a while they thought maybe it was a stressed liquid. They were trying to figure out what phase this was. And pretty recently, farther and farther from when I was in graduate school, but not long before I was in graduate school, the argument was finally successfully made that glass is its own phase of matter. So there's a glass phase. And so their example in the textbook of an amorphous solid isn't a very good one because that's actually its own phase. So amorphous solids are very tricky. So the more standard examples would be there's amorphous silicone that's used for things like solar panels. And there is also plastics or polymers. They are amorphous. There's not a repeating structure within the solid. It's kind of a chaotic mishmash throughout them. And it was actually plastics researchers that made the case for glass being its own phase, because polymers transition through the glass phase and into the solid phase as they cool. And so there was this distinct phase with specific thermodynamic properties that were very different from a solid or liquid. And it literally took someone retiring who was very influential in the field for this research to finally be accepted. So, science isn't always perfect. It is done by people. But eventually, the correct ideas can win out. It might just take a generation. Someone has their entire career built on glasses being a stressed liquid, and they're the person that keeps basically refereeing your paper and deciding whether or not your ideas get to be published. That can cause a delay, and it literally was the case. And someone had to retire, and then boom, now we all accept glass as its own phase of matter. And it was a tidal shift that was almost immediate. All right, so amorphous solids are tricky, they're complicated, but essentially they just don't stack in an orderly pattern. That's the main thing you just got to remember about them. Crystalline solids stack in an ordered pattern, and there's a number of different categories. And so there's something like an atomic solid. And by the way, the names give away exactly what they are. And so these are just atoms that are stacked, so non-metal atoms specifically, because if they are metal atoms, guess what we have? We have a metallic solid. That's right. The very next one on the list here, we got metallic solid. So atomic, they give the example here of xenon. So if you get xenon gas cold enough, it will liquefy, bring the temperature down, or if you up the pressure, it'll turn into a solid. And the melting point of this solid is 161 Kelvin. So yeah, it's going to need something colder than your freezer at home to make this happen, but it can. And the reason that it has such a low melting point, it has low intermolecular forces. It has just London forces, and it's a small particle. And so if you were to use something like helium, it's going to have an even lower melting point because it's a smaller particle. It has even less surface area for London forces to take effect. And so we can solidify things like noble gases, but as their size gets smaller, that becomes more difficult. So next we have metals. We've all seen metals, aluminum, iron, so on and so forth, silver, gold, and things like jewelry. And so the example they give here is silver. And so again, it's just an orderly stacked pattern. All of these atoms, by the way, whether they are non-metals or metals, they're just spheres. So we're just literally just stacking spheres together. So I always make the joke about the McDonald's ball pit. If you've seen a McDonald's ball pit, you've seen a solid on the atomic level. And so what we have here are metals, and they're trying to push electrons on each other. We've talked about this before with metallic bonding. There are more forces that play here than just London dispersion forces. There's metallic bonding. And so something like silver has a melting point of about 1200 Kelvin, or about 1000 degrees Celsius. So you got to get this pretty toasty, definitely more than the xenon. And then the most strongly bound together type of solid is typically going to be these ones that are covalent network. And so this would be something like carbon and the diamond form. Now no one has really, actually, as far as I know, melted diamonds, but the theoretical temperature is 3,820 Kelvin, and that's a maybe. Like no one, as far as I know, no one's done this, and you'd have to do this with no air, otherwise it would essentially just catch on fire. And this is tricky because it is 100. This is all one molecule. This is one covalent molecule. So when we say a covalent solid, we mean like one large covalent molecule. So they are all covalently bonded together. These are not intermolecular forces holding this thing together. These are covalent bonds. That's why they're so much stronger of a solid. So I can use diamonds for cutting because they're a very strong solid because they have something much stronger than an intermolecular force. They have a bonding force, full-on covalent bonding. Okay, and so next we have ionic compounds, and this is where it starts getting a little tricky because now we're stacking spheres of different sizes. And so look at that, my example right there, boom, right off the bat in chapter 12. Thank you, book. Sodium chloride, NaCl. Now the cations are always going to be small, the anions are always going to be large because as you add electrons on to an atom, it becomes an anion. It's going to increase in size. If you take electrons away, form a cation, it's going to become smaller. And so typically what you're going to see, I mean, there's probably some weird example, but generally, cations are small, anions are large. So these are our chlorides in the green here. These little orange spheres are sodiums. And so the stacking becomes a little more intricate because now we're fitting together different sized pieces, whereas before, we're stacking stuff that's all the same size. Now, these silver atoms might not be the same size as the xenon, but they're only surrounded by other silver, so by scale, They're all the same size within this structure, and all the xenons are the same size within this structure. But now we have pieces of different sizes. And this will come up as well with metal alloys, where we start mixing together different metal atoms, but I'll talk about that in a subsequent video. But it does complicate the stacking of these particles. And then what we have are molecular solids. So these were ionic solids. Now we have molecular solids. And so these are groups of molecules. So these are not covalent solids. These are covalent molecules that have solidified with neighbors. Okay, this is sometimes people get a little tripped up here. So this is not one water down here in ice. This is multiple waters stacked together, whereas carbon was bonded together in one large molecule of diamond. So that's the difference. And so again, the different classifications, it just depends on, well, our properties are going to depend on what our intermolecular forces are holding this solid together. If it's London forces, they're going to have a lower melting point than if it's dipole-dipole, and that's going to have a lower melting point than if it's hydrogen bonds. They're all going to be very poor conductors, and what else can we say about them? I mean, that's pretty much it. They don't conduct electricity by themselves, and they tend to have low melting points. Even water is considered a low melting point compared to, say, something like sodium chloride, which is about 1,000 Kelvin, so pretty toasty. And in the molten state, you can use them to conduct electricity, so that's why they talk about like molten salt batteries, things like that. Those are some big ideas out there for like high level, grid level energy storage. And, you know, those ion-ion attractions are very strong, so that creates a high melting point. Whereas these were just bumping neighbors apart, so it tends to take less energy. They're not going to conduct electricity on their own. And so what do I mean by like a low melting point? Well, you know, water, 0 degrees Celsius. What else we got? CO2 up here, it's 195 Kelvin, so that's below room temperature. And they can be a little higher than room temperature, a little lower. There's some wiggle room in there. Like this is below room temperature for sure on this guy, because that's pretty much a very volatile liquid at room temperature, typically with the CHCl3 there, excuse me. And then amorphous solids, like I said before, they're just tricky. Don't worry about them too much. Just understand that you're not going to have this common stacking structure within an amorphous solid. That's what defines it. See how it's kind of a chaotic structure there, and it turns out it's a glass, but you know, whatever. It's like I said, it's still a pretty recent idea that glasses were their own phase. So hopefully the next edition of the textbook will catch on to that. Alright, so these are the different types of solids. And again, they're just stacking together. That's and that's how we get that high density. We're fitting them together with as much density as we can, pretty much, because there are repulsive forces between the nuclei here, but there are attractive forces that hold it together. So you can't push them too close, but they're not going to get too far away. Alright, and so next we'll talk about how we diagram the stacking structure, and that's called the unit cell. So that'll be the next video here.